So we continue from where we stopped in the first lecture. In the first lecture, we have defined what we call the general topology, and I gave definition of discrete topology, trivial topology, upper topology, and we did some proof. And I rounded it off with the closed set. So today we are going to continue from there. Today we are going to be talking about the basis of a topology. But before then, I will do two exercises on how to show that a space is a topological space. So now I'm going to write an example on the board. They are non-trivial example, and we are going to solve amicably. So exam exercise. Let X be a non-empty set, right? And let infinity be a member of X. Let infinity in X be a particular element of X. Verify whether the following form a topology on X. The first one is topology defined as A S, so that infinity is an element of A, or A complement is finite. And the second one is AS, such that I need to AS such that A is empty, or A complement A is empty, A is the empty set, or A complement is finite or countable. So we are going to show these two, whether it's a topology on X or not. So let's come to the first one. I have the topology defined as A in S, so that infinity is in A, or A complement is finite. So now we want to show whether or not this is a topology. And to show that this thing is a topology, we have to show three things. The first thing is we have to show that the empty set and the host set is there, and the arbitrary union of every element here is also in the topology. Then what you call finite intersection as well. Now the first thing is we want to check whether the empty set is here. So the empty set, is it in this one? That is the first question. This one is there's a mistake here. This one means it's not a member. It's not a member. So now the empty set, infinity, this particular element of X is not an element of the empty set, because the empty set is empty. No element is in the empty set. So because infinity is not in the empty set, it means that the empty set is a member of the topology. So that means the empty set is in the topology. So for something to be inside this set, for something to be inside this set, for an element to belong to this topology, number one is either infinity is not a member of that element, or the complement is finite. So I need to check whether the empty set or the host set is in the topology. That's the first thing we need to show. So now for the empty set, no element is there, and since there's no element there, it means that the infinity will not also be in the set. So that means the empty set does not contain this element, and it means it's in the topology. Now it remains to check for S. S, obviously infinity is in S, so I can't use this. But let's take the complement. The complement of the whole set. The complement of the whole set is empty. The complement of the whole set is the empty set, because S is the whole space. If you take the complement, you have the empty set. So since I have the empty set does not have any element, so we say it's finite. The empty set is finite. The empty set is finite. So that means that the complement of X is finite. And since it's finite, you can see for an element to be in the topology, to be in this topology, it's either it does not have this or its complement is finite. So since the complement of the whole set is finite, it means that S also belongs to the topology. So therefore, the empty set and the whole set is in the topology. That is for the first case. Now for the second one, arbitrary union. Let AI so that I in I be a collection of members of topology. We want to prove that the union, arbitrary union of this AI will also be a member of the topology. So now, how do we do it? We have to consider case. Now, the first case 1. The first one, let's talk about the first case 1. Case 1 is suppose infinity does not belong to all the AI. That's the first case. Now, does not belong. Suppose infinity does not belong to all the AIs. So, what will happen for all I in I? Suppose infinity does not belong there. So, what happens is that for the first case, since for the top, what we have in the topology, number 1 is for an element to be a member of the topology. For an element to be a member of the topology, what happens is that it's either this infinity is not in the element or its complement is finite. It's either this infinity does not belong to this element or the complement is finite. So that's why I have to consider the first case. I think I will have to consider 2 cases, and the second case will be 2 as well. So for this case 1, suppose all the whole collection I've taken obey this law, because there are 2 laws, there are 2 principles that it has to obey. The first one is this one or this one. So for the first one, if all the collection I've taken, is with respect to this one, what will happen is that that's the first case I'm talking about. Suppose infinity is not a member of AI for all the I's. We want to show that the union will not be there. So now, since infinity does not belong to all the AI for all I in I, since infinity does not belong to any of them, it means that infinity too will not belong to the union. If you take the union of the whole set, infinity will not also be there. Why? Because it will not be there. Why? Because each of them does not have infinity. Take for instance, if I have 3 sets A1, take set A1, I have 2, 3, 4, A2, 3, 4, 5, and A3, maybe 4, 5, 6. 4, 5, 6. Now, let me now take an element 7. 7 is not in A1. 7 is not in A1. 7 is not in A2. 7 is not in A3. If I take the union A1 union A2 union A3, if I take the union of A1 union A2 union A3, what am I going to have? I'm going to have 2, 3, 4, 5, 6. So you can see, because 7 does not belong to their individual set, it does not also belong to their union. That's what I'm saying here. If every collection I've taken here does not contain infinity, infinity will not also be in their union. So since infinity does not belong to their union, as we have said before now, we have said that for an element to belong to this topology, it's either infinity does not belong to it or the complement is finite. So since infinity does not belong to this, it means that it's also a member of the topology. So it means that union of I in I of AI belong to the topology. Now, the second case, case 2. Case 2. So for the second case, case 2, now, why am I bringing up this case? The reason why this case is showing up is because of these two things. You know, for an element to be in this topology, as I've explained, infinity will not be in the element. You can say A in X. Infinity is not in the element, or the complement of the element is finite. So because of these two, that's why we are taking cases. Now, if everything I have taken here, if all the AI I have taken, it does not contain infinity, it works. And suppose, now the second case, what will be the case 2? Let us take this second condition. Now, suppose what's it called? AI complement is finite. Suppose AI complement is finite for all. AI complement is finite for all I in I. Now, suppose all of them. Suppose everything I've taken here is satisfying the second condition. How do we solve? How do we show that the union? We want to prove that. We want to prove that the union of all the AIs for I in I is a member of the topology. Now, for this case, I will take the complement. I will check whether the complement of this thing is finite. If the complement is finite, then we are good to go. Now, let us check. Union of I in I of AI complement. When you take the complement here, this one will be equal to from De Morgan's rule. This one will change to intersection. Intersection of I in I of AI complement. Now, note, AI complement is finite. You can see all these AI are members of the topology, so they satisfy these two conditions. It means that their complement is finite. So AI complement is finite. You are now taking the intersection. The intersection of a finite set is still finite. The whole intersection you are taking is finite because see, from the Morgan's rule, this one has changed to intersection and this one is taking AI complement now. So this AI complement is finite, and because it's finite, I'm now taking intersection of a finite element. The intersection of a finite element is still finite. So what does that mean? Note that AI complement is finite, and it means that the arbitrary intersection of a finite element is still finite. Is finite. Arbitrary intersection of a finite element, of a finite set is finite. So because the intersection of all these ones is finite, what does that mean? It means that therefore the union of all these ones of the AI complement outside is finite. And if it is finite, what does that mean? It means that the union of I in I of AI is an element of the topology. So The third case is now that I've done two cases now. The first case, if every element every collection I've taken here satisfy this one, we have proved that the union is in the topology. If the finite intersection, if everything I've taken here satisfy this second one, I've also proved it. Now, suppose the collection have some of this and some of this. Now, this is how we are going to do it. I don't want to rub off the question. Now, suppose now after I prove that one, suppose here is this I naught in I, so that suppose here is this I naught in I, so that AI naught, does not, so that infinity rather does not belong to the AI naught. So we know that infinity does not belong to the AI naught. Now we know that AI naught is a subset of its union of the AIs of I in I. We know that this AI naught. What I'm trying to say is that from the collection I have taken here, from the collection, I said that let AI, so that I in I be a collection of members of the topology. So now let's continue. Now, what I'm trying to say is, I've taken a collection of members of the topology. So if all of them satisfy this one, that's case one. If all of them satisfy this second one, this one, that's case two. Now, if some of them, so if some of these ones, let's say this, I have A1 to A10. A1 to A10. This AI means, for I and I, means that A1, A2, A3, and on like that. To explain it in a simple way. This is just what it means. Imagine I have A1, A2, A3, A4 to A10. What case 1 is trying to say that I just rub off now is that all this A1 to A10 satisfy this. And I proved that the union also is in the topology. Now, for the case 2, it means that all this A1 to A10 satisfy this. And I've also proved that the union is also in the topology. Now, imagine A1 satisfy this one. The remaining satisfy this one. Imagine A1 satisfy infinity is not in A. And A2 to A10 satisfy the complement is finite. What does that? That's what I'm trying to say. Suppose there is this I naught in I. This I naught means a particular set I naught in I, so that infinity does not belong to AI naught. What that one is saying is that this I naught might be 3, maybe A3. Suppose A3 satisfy this one and the other one satisfy this. So that's what I want to do now. So suppose here this I naught in I, so that infinity does not belong to AI naught. We want to prove that they are unions. So if AI naught A3 is inside A1 to A10, you get my point. So A3 is inside A1 to A10. So what this one is, the next thing I have written now is saying that A3 is inside, or is a subset of the union of AI, so that I start from 1 to 10. That's what I've written here. Suppose here is this I naught. This I naught can be anything. It can be maybe 3, like I've explained, A3. It can be A5, it can be A7, it can be A10. So this I naught is just a notation that suppose one of them, suppose one of them satisfy this one, and the others, the remaining ones, excluding that one, satisfy this. So, but we know that A3 will be a subset of the union of everything. What is this one trying to say? Imagine I have A1 to be maybe 1, 2, 3, and I have A2 as well, A2 to be 3, 4, and I have A3 as well, A3 to be 4, 5. The union of A1 union A2 union A3, what will it be? A1 union A2 union A3 will be A1 union A2 union A3 will be equal to 1, 2, 3, 4, 5. Obviously, you can see that A1 is actually a subset of A1 union A2 union A3. A2 is also a subset of A1 union A2 union A3. A3 is also a subset of A1 union A2 union A3 as well. So, because of that, because of what I have written here, because of, as you can see, every set here is a subset of their union. So, A3 will be a subset from the illustration I'm giving here. A3 will be a subset of the union of I starting from 1 to 10. This one means that A1 union A2 union A3 to A10. That's what it means. So that's what I'm trying to say here. So since this I naught is one of them, it's part of. Now coming back to what I'm doing, since this I naught, this AI that I have here, so the I is in I. Since this I naught is one of them, so it will also be a subset of everything, because the I naught is also inside here. It will obviously be a subset. So since it's a subset, what are we going to do now? What we are going to do now is that we will now need to take the complement. So if you take complement, if you take the complement, what will happen? I think I'm going to I need to write AI naught. Suppose there is this I naught in I, so that AI naught is finite. That's what I need to write. So that AI naught is finite. So what will happen? What will happen is that AI naught is inside the union of I in I of AI. The union of I in I of AI. So what will happen? You will now take the complement. If you take the complement of both sides, this one will become AI naught complement. When you take complement, this thing will change to superset of union of I in I of AI, everything complement. So let me write it where this one will be union of I in I of AI complement, and this one will now be inside AI naught complement. So since you can see what I have here, the union, arbitrary union complement, is a subset of this, but this one is finite. So what does that mean? It means that if AI naught complement is finite and all this one is a subset of this, it means that this one too is finite. It means that union of I in I of AI complement is finite. It's finite as well. And since it's finite, what does that mean? It means that the union, arbitrary union of this one, belongs to the topology. So now, what is the essence of this third case in quotes? The essence of this third case is that if case 1, no, I told you case 1 satisfied this, case 2 that I've given here satisfied this. Now, if everything you have there, you can find one A complement that is finite in the whole, let me try to explain what I'm trying to say. AI, so that I is in I. Right? Now, these are the collection I have taken. like I've explained, A1 to, let's say I have A1 to A10. So since I have A1 to A10, if one of them, maybe let's say A1, is such that the complement is fine, that it satisfies this one, and the others satisfy this, it will still be correct. Even if it's not one, if two of them, let's say A1, A2, without loss of generality, I just show for one that assuming you just have one of them, even though it's two of them, I will bring the two out here. I will now write, I would have written A1 union A2 is inside everything. Then I will do all these things. It will still be satisfied. So my point is, even though it's more than one, even though it's more than one element or one set, even though it's more than one set that satisfy this, the proof will still be correct without the loss of generality. So that's what I'm saying. So from there, I'm drawn with the arbitrary union to be. I'm drawn with arbitrary union is also a member of the topology. Now the third thing I need to do now is to prove for the finite intersection. Now for the finite intersection, now what I'm going to do is, for finite intersection, let A1 and A2 be elements of the topology. Let A1 and A2 be elements of the topology. So we want to prove that. So it suffices, of course, from the first lecture, I already told you that whenever you want to prove finite intersection, you just take 2 and do A1 intersection A2 and prove that it's there. So we want to prove that. We want to prove that A1 intersection A2 is A1 intersection A2 belong to the topology as well. That is what we want to prove. So now we also consider case here, case 1. What is this case 1 talking about? Let's suppose rather infinity does not belong, that is, this element does not belong to both A1 and A2. If it does not belong to both A1, in fact, if it does not belong to only one of them, it will not belong to their intersection. So let alone it does not belong to the two of them. If suppose infinity does not belong to A1 and A2, it means that suppose infinity does not belong to A1 and A2, it means that this infinity will not also be in their intersection. Since infinity does not belong to their intersection, it means that they are also a member of the topology. Now, for the second case, case 2, what will case 2 be? Case 2, we say that case 2 will be that suppose A1 complement and A2 complement are finite. A1 complement and A2 complement are finite. We still want to prove that A1 intersection A2. So now let's check. What will be A1 intersection A2 complement? For me to show that an element belongs to this topology, it's either it satisfies infinity does not belong to the element or to the set rather, or the complement of that set is finite. So now A1 intersection A2 complement. This one will be A1 complement by the Morgan's rule union A2 complement. Now A1 complement is finite and A2 complement is also finite. The union of just two complements, the union of two finite sets, is finite. So this one is finite, and because it is finite, it means that all this one belongs to the topology because their complement is finite. So it means that A1 intersection A2 is also a member of the topology. Now, then to round off this question, to round it off, to round it off, So to round it off, the third case, case 3, let infinity. In fact, it has this third case has been in this one and this one. Let infinity not be in A1 and A2 complement is finite. Because infinity is not in A1, it means that infinity will not be a member of A1 intersection A2. Since it's not in A1, it can never be in their intersection. Intersection means common element. So if infinity is not in A1, it cannot be in their intersection. So by so doing, A1 intersection A2 will be in the topology. Or even if you want to prove alternatively, if you want to show this one, alternatively, now see if I have done A1 intersection A2 complement, what would I have gotten? I think the alternative own we don't need an alternative here. So that's all. That's all. So therefore, which is equal to this A in S such that infinity is not in A or A complement is finite is what? Is a topology. It's a topology. Now let's come to the second one. The second one, I have A is in S such that A is empty or the complement is finite or countable. Now, don't forget, when you want to prove that something is a topology, what will happen is that you will show there are 3 properties you have to show. Number 1, you show that the empty set and the whole set belong to the topology. Number 2 is that you will have to show that arbitrary union of open set of the element here is also in the topology, and the third one, finite intersection. So now let's start with the first one. Obviously, the empty set is in the topology trivially or by definition. So trivially, the empty set is in the topology trivially because from the definition you can see A is empty or the complement is finite or countable. We have that. Now, the second one, the whole set, of course, the complement of the whole set is also empty. And this one is finite or is countable. This is finite and it's also countable. So, because every finite set is countable. So now, this is also finite. It also means that S also belongs to the topology. So therefore, the empty set and the whole set belong to the topology. Now, the second thing I want to do is that let AI, so that I in I be a collection of what? Of members. Be a collection of members of what? Of the topology. So, what do we want to do? We want to prove something. We want to prove that the union, the arbitrary union of all these things will also be in the topology. Right? The arbitrary union will also be there. So now, what will happen is that since this is what I have, what will happen will be that we want to prove that the union of I in I of AI belong to the topology. And without loss of generality, just let all the AI satisfy the second condition, because if you satisfy this one, is trivial. So now, without loss of generality, without the loss of generality, let all the AI complements be countable for all I in I. So I will now take union of I in I of AI complements. So this one will be equal to the intersection by the Morgan's rule of I in I of AI complement. And since this is what I have, intersection of I in I of AI complement, since this is what I have, what will happen to this is that the AI complements are countable. All the AI complements, they are countable. Everything here is countable. Intersection of countable set is countable. Arbitrary intersection of countable set is also countable. So this one is countable. So since I have this, the implication is that it means that the union of I in I of AI is a member of the topology. Now the third one we want to do here is let A1 and A2, we want to do finite intersection, A1 and A2 be a member of the topology, right? So if they are members of the topology and A1 complement and A2 complement are countable, right? Without loss of generality. Without the loss of generality. Without the loss of generality. So, what will happen now? What will happen will be that I want to do A1 intersection A2 complement. If I can show that this is countable or finite, it means that A1 intersection A2 is a member of the topology. So A1 intersection A2 complement, this one will be giving me A1 complement union A2 complement. A1 complement is countable, A2 complement is countable. The union of two countable sets is countable. So this is countable. So therefore, it suffices that A1 intersection A2 is countable. It means that A1 intersection A2 is countable. So therefore, or thus, this is a topology. So we are through with the two examples I gave, and of course you yourself can testify that it's not